Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 27 of Algebraic Topology. In our previous lecture, we studied the relation between homology and attaching cells, and then we calculated the homology using this relation of some objects. For example, projective plane, real projective plane, complex projective plane, and other objects. So in today's lecture, we will first discuss what are manifolds. So the discussion is not going to be very technical. So basically we will review some concepts about manifolds. And then we will continue in our second section of today's lecture with the definition of CW complexes. And in the next lecture, we will see that how we can use these definitions to calculate the cellular homology. So let's start with the definition of manifold. An N manifold, so here N stands for the dimension of the manifold. So here, okay, so an N manifold is a Hausdorff space. So of course Hausdorff space means, as a topological space, it's a Hausdorff space such that each point in M has a neighborhood homeomorphic to Rn. Okay, so for example, the planet Earth is a 2 manifold because locally when you are standing at some point on Earth, then for example in a room, you can see that the room is flat. So you can say that locally this is homeomorphic to R2. Okay, so similarly if you are talking about an N manifold, then locally it should look like an Rn. Okay, so let's see how this definition will be applied to a two-dimensional case. Okay, so it says that it's a, for example, when n is equal to 2, so it says that it's a 2 manifold if each point in M has a neighborhood homeomorphic to R2. Okay, so in this diagram you can see that we have a subset of R3, so this M, and we want to see that whether this subset M of R3 is a 2 manifold or not. So to check that if this is a 2 manifold or not, we have to see that if each point in M has a neighborhood homeomorphic to R2. Okay, so consider this point P. So in other words, now we are looking for some neighborhood of P which is homeomorphic to R2. Okay, so that's what the definition is. Now there are many examples of manifolds around us. So for example, torus, Klein bottle, sphere, real projective plane, etc, etc, etc. So in particular these are all examples of two manifolds because these are two-dimensional spaces. Now there are two kinds of manifolds, namely the manifolds which are orientable and the manifolds which are non-orientable. Okay, so we are not going into the technical details of the definition of orientability, but roughly speaking, a manifold is orientable if it has a consistent choice of orientation. So for example, on this in this animated diagram, you can see that there is a unique normal vector at each and every point of this surface. Okay, so in the case of surfaces, you can say that a surface is orientable or a two manifold is orientable if you have a unique normal at each and every point. But on the right hand side, we can say that we have a Mobius strip. Okay, and now over here we have a policeman who is patrolling on this Mobius strip, and you can observe that this policeman will be at one point on the top of the Mobius strip, and moving along it will come at the bottom of this Mobius strip as well. So in other words, you can say that there is not a unique normal vector at any point of the Mobius strip. Okay, so we don't have a unique normal vector, or we can say that there is no orientation. Okay, so for example, we don't know what is the upside and what is the downside. Okay, so we don't have any concept of orientation in the case of Mobius strip. So Mobius strip is an example of non-orientable manifold, and for example, a sphere is an example of an orientable manifold. So as I said earlier, that a sphere is going to be orientable. Similarly, torus is an orientable 2-manifold, and Klein bottle is non-orientable 2-manifold, and similarly real projective plane is also non-orientable 2-manifold. Now we know that we can obtain a torus by identifying opposite sides of a rectangle. Okay, so for example, in this case, if we identify the side A with side B, so in other words, we are just saying that take the topology on this square and take the quotient of this topology, the quotient which will identify this side with this side and this side with this side. So the quotient topology is going to be homeomorphic to this torus. Okay, so the purpose of this example is is it possible that we can obtain any manifold in this way? Okay, so let's continue with a more non-trivial example of two torus. Okay, a torus with two holes. Can we obtain a torus by identifying sides of some polygon, if not square? So the answer to this question is yes, we can. Okay, so the process is very simple. So we know that this one square, okay, so with these two opposite sides identified, is a one torus, and similarly take another torus. Okay, so now if I want to obtain a two torus, so what do I do is I cut down these two tori from these corner points. Okay, so cut them and then join them in the following way. Okay, so this is the side A, so this is going to be the side A, this is the side B, this is the side B, this is side A, and then once again this is side B, and we will join this corner with this corner. So in other words, this side is going to be C and then D and then C and then D. Okay, so these are two tori and we joined them in this way. Okay, so of course this is one torus, and on the other side we have one torus. So now we cut them down and we joined them in one polygon, and when we identify the opposites, the sides with the same labels, then we obtain this two torus. Okay, so that gives us a hope that maybe it's possible for each and every manifold, or for example for each and every two manifold. Okay, so that we can write or we can obtain a two manifold in this way by identifying sides of a polygon. Okay, so let's go on and continue with this discussion. So in general, just like we obtained a two torus from identifying the sides of an octagon, and one torus from identifying the sides of a square, we can go on and similarly we can obtain a three torus. Okay, and up to so on. So the procedure of this is going to be the same. Take another torus. Okay, so in other words, take another square with sides, let's call them G and F, and then cut them down and glue them, and then we will obtain a polygon like this, and identifying the same labeled sides of this polygon will give me a three torus. I can continue with this process of adding more and more torus, and in general I can obtain a torus with n holes. Okay, so we can obtain an n torus by identifying sides of a polygon. So in general we have this result about the orientable manifolds, that consider a 4G gone, okay, so a polygon with sides 4H, okay, so W in the plane whose edges are labeled as alpha 1, beta 1, alpha 1 inverse, beta 1 inverse, up to so on. Okay, now identify the sides of this polygon, and in other words we are saying that take the quotient of this topology under some equivalence relation. So construct the quotient space M of W by identifying edges according to the labels. Okay, so just identify the sides according to the labels. So this goes here, up to so on. Okay, now in this way we will obtain an orientable manifold. Okay, so in precise words we can say that every compact connected, okay, so we impose these conditions just to make sure. So for example, if it is not connected, then we can talk about the two connected components separately. Okay, so similarly if it is not compact, then it is not possible. Okay, so these two conditions are required for this result to work. Okay, so of course we know what is a compact topological space. So if every open cover has a finite open subcover, and what is connected topological space. Okay, so basically a manifold is a topological space such that for each point P there exists a neighborhood which is homeomorphic to Rn, or in case of two manifold, homeomorphic to R2. Okay, so every compact connected two manifold which is orientable is homeomorphic to M. So what is M? So we obtain this M by identifying the edges of this 4H gone. Okay, so given over here. The surface M is called a sphere with H handles. So why a sphere with H handles? So let's consider some particular cases. So if H is equal to 1, then M is a torus. So in other words we can say that it's a sphere. Okay, so H is equal to 1 case, it's going to be a sphere with one handle on it. Okay, so this is the same as a torus. Okay, similarly when H is equal to 2, then we will have a picture like this. It's a sphere with two handles, and this is the same as this diagram, and this is the same as this diagram. So in other words we will get a 2 torus, which is homeomorphic to a sphere with two handles. Okay, so that's why it is called a surface M is called sphere with H handles. Okay, so when H is equal to 0, so this is a special case, then M is obtained by identifying the boundary points of W to a point, and in this case M is homeomorphic to S2, or just a 2 sphere. Okay, so now we have this important result where we say that every orientable manifold can be obtained by identifying the sides of a polygon, and it tells us more than that. It's also telling us the geometry of the object as well. So it says that if you want a surface with H handles, then we should consider a 4H gone, and we should identify the sides according to this rule. Okay, so this is an important result about the two manifolds. Let's continue our discussion about the manifolds, and let's go to non-orientable manifolds. So we have a very typical example of a non-orientable two manifold. It is example of a real projective plane. Okay, so we also know that a real projective plane can be obtained by identifying the sides of a square, but in this case the directions of the arrows are different than the direction of the arrows in the torus case. Okay, now of course we want to see that is it possible that in the case of non-orientable manifolds can we obtain any non-orientable manifold by identifying the sides of a polygon? So let's go on and continue with the examples. So we have another example of a non-orientable manifold, which is Klein bottle. Okay, so a Klein bottle can be obtained by identifying the sides of this square, and notice that the orientations of the sides is different than the orientations of the sides for the torus case and the real projective case. Okay, so so far we have seen two examples of non-orientable manifolds which can be obtained by identifying the sides of a polygon. Now this result says that it's possible that we can obtain any non-orientable manifold by identifying the sides of a polygon. So consider W prime, which is a 2n-gon, and the sides are labeled as alpha 1, alpha 1, alpha 2, alpha 2, alpha n, alpha n. And consider the surface M prime, which is obtained by identifying the edges according to the labels. Of course, identify the edges labeled as alpha 1, alpha 1, identifying the two edges labeled as alpha 2, alpha 2, up to so on, up to alpha n, alpha n. Now we have this important result which states that every compact connected two manifolds. So once again we are imposing this condition because otherwise the statement is not true. So a manifold is a topological space, so we are imposing these conditions on that topological space. Okay, so every compact connected two manifold which is non-orientable is homeomorphic to M prime. Okay, so the surface M prime is called a surface with n cross caps. Okay, so we have a very typical example. If n is equal to 1, then M prime is real projective plane, and the other examples are going to be very non-trivial. So let's continue with our next operation. So now what we are going to do is, given two different two manifolds, now we are going to define an operation that will combine them together to define or to construct another manifold. So this is called connected sum. So we are going to define connected sum of two manifolds. So there are several steps for this procedure. So in the first step you have two manifolds. Let's call them M1 and M2. Now we choose two subsets of M1 and M2, and each subset is homeomorphic to R2. So for example, in this diagram you have M1 over here and M2 over here. So let's choose this U1 and let's choose this to be U2. Okay, so in the next step what we are going to do is choose the disks D1 in U1 and D2 in U2. So in M1 and M2 we have this U1 and we have this U2, and this is the disk D1 and this is the disk D2. Okay, so so far we have chosen two manifolds and subsets U1 and U2 of M2 which are homeomorphic to R2, and then we chose two disks inside those subsets U1 and U2. Now choose a homeomorphism from the boundary of D1 to the boundary of D2, which is inside M2. Okay, so this is M1, this is M2, this is my U1, and this is my U2, this is D1, this is D2. So choose a homeomorphism from this dotted line, which is going to be a circle, to this dotted line, which is going to be a circle. Okay, so if you have this homeomorphism, then we can attach this M1 with M2. Okay, so how we attach them? So using this homeomorphism. So remember that we have done procedures like this when we were discussing how to attach a cell to a topological space. Okay, so now in this case we are attaching two manifolds, M1 and M2. So so basically glue this thing with this thing. So glue this circular boundary with this circular boundary, and of course delete whatever is inside this disk. Okay, so roughly speaking, what's the procedure? Okay, so the procedure is very simple. Take two manifolds M1 and M2, choose two disks inside M1 and M2, delete the interior of the disk and glue the circles or the boundaries of these disks, and we will obtain M1 hash sharp M2, and this is called the connected sum of M1 and M2. Okay, so you can see that we made some choices when we were trying to construct the connected sum. So for example, we said choose open sets U1 and U2, and then we said choose disks D1 inside U2 and D2 inside U2, and then we said choose a homeomorphism. So we made some choices. In fact, when we are constructing the connected sum of two manifolds, then this is independent of the choices. Okay, and of course it means that if we made some other choice of for example open sets UIs or some other choice of homeomorphism, then the resulting connected sum is going to be homeomorphic to some other choices of UIs and the homeomorphism. Okay, so that's how we define connected sum. So now what we can do is, given two manifolds, I can construct another manifold using those two manifolds. Okay, so the connected sum can be thought of as surface obtained from M1 and M2 by removing the interior of D1 and D2 and then gluing along the boundary of D1 and D2. Okay, so once again this is the same thing. So let's see what can we do with this special operation of connected sum. Okay, so here's what we can do. So given two tori, I can take the connected sum of those two torus and I can construct a two torus. Okay, so what's the procedure? So the procedure is very simple. Take a disk inside one torus, take another disk inside this one torus, remove the interior and then join the boundaries. Okay, so join the boundaries of these two tori, and what we will get is a two torus. Okay, so similarly I can connect another torus with this and I will get a three torus, and up to so on, and in general we can obtain an n torus from procedure like this. So that's the power of this operation of connected sum. So given manifolds or two manifolds, we can have their connected sum and then we can obtain other manifolds. Now let's see the situation in a planar diagrams. Okay, so we know that a torus can be obtained by identifying the two sides of a planar square, and similarly if we have two torus we have two squares. So how to obtain the connected sum of these two tori and the result such that the result is a two torus? So the procedure is very simple. So take a disk inside this one torus and take another disk inside this one torus. So this disk is going to be along this part. Okay, so let's label the sides of this octagon. So this is the side C, this is the side D, this is the side C, this is D, this is A, this is B, this is A, and this is B. And similarly we have this disk inside the torus and it will be along this side. Okay, so when we cut them then we have and glued them, then we have this octagon, and we know that by identifying the sides of this octagon we get a two torus. So that's what the situation looks like in plane. Now consider another non-trivial example of connected sum, where we are going to consider the connected sum of a real projective plane with itself. Now we shall see that this connected sum of a real projective plane with itself is going to be Klein-Bottle. So let's see in the planar diagrams how this is possible. So we can consider a real projective plane to be a disk in plane, and similarly for the second projective plane. Now we can follow the same procedure, and we can obtain a shape like this. Okay, so we cut them and we glued them along these disks, and that's the line, and that's side A, and that's the side A, this is the side B, this is the side B. Okay, now we can ignore this direction, and we can consider the following diagram. Okay, so this is the side A, side B, side B. Now consider this side with side, and let's call it C. Okay, now if we identify, because this is B and this is B, if we identify these two sides and write down this C twice, okay, so unidentified, okay, so because when we will identify the two C's, then we will obtain this picture. Okay, so let's identify this B and B, and what we will obtain is this diagram. Okay, so you can see that this A and C are going to the same vertex, so this A and C are going to the same vertex. Now consider another A, and in this case this A and C are going in the same flow. Okay, so in other words, we can say that this C and this A are going into the same flow. Now let's talk about this B. Now we see that this A and B are going into the same flow, so this A and this is side B are going into the same flow. So that's what we obtain by identifying the sides B and writing down this C twice. Of course, when we will identify the two sides of C and write down this B twice, then we will obtain this diagram. Okay, now of course we can ignore this B, and what we will obtain is basically a square, and the orientations are, so two sides are going in the same way and two sides are going in the opposite way. So you can see that it is the same as this square which we have already seen, and which we have already seen that it is a Klein-Bottle. So in this case the two arrows are going into the same way, and two opposite arrows are going in the opposite direction. So this is the Klein-Bottle. Okay, so that's how we obtain a Klein-Bottle, by taking the connected sum of two real projective planes. Okay, so this operation hash is commutative and associative, and moreover for a compact connected two manifold, which we can say that it's a surface, we have this result that M sharp S2, the two sphere, is homeomorphic to M2. Okay, so for those who are familiar with the idea of group, we can say that this operation is commutative, associative, and this S2 acts like the a right identity of this set. Okay, so we have the following important result then: every compact connected two manifold is homeomorphic to either two sphere, torus, real projective plane, or a connected sum of several copies of the latter two. So now we have an extremely important result about the manifolds. It says that of course this technical condition of compact connected is there. So every two manifold is homeomorphic to connected sum of torus or real projective plane. Okay, and also we have the following relationship, that the connected sum of real projective plane and one torus, so a torus with one hole, is homeomorphic to the connected sum of 3 copies of real projective plane. So that's why we can't have mix connected sums of real projective plane and torus. So whenever there is a mixed connected sum, so when I'm saying mixed, it just means that this real projective plane and this T cannot appear together, because whenever they will appear together, then we can replace it with the connected sum of 3 copies of real projective plane. Okay, so every compact connected 2 manifold is homeomorphic to either 2 sphere, torus, or real projective plane. So we know that there are 2 types of manifolds, orientable and non-orientable. So in particular, this result can be made more applicable or more detailed in the following way, that if X is orientable, then this X is homeomorphic to connected sum of these mi's, and each mi is basically a torus. Okay, so the number G is called the genus of X. So in general, a compact connected orientable 2 manifold looks like the following. Okay, so now from now on, whenever we want to sketch an orientable 2 manifold, then it will look like this, because we know that every orientable, of course with the condition of compact connectedness. So if X is orientable, of course with the condition of compact connectedness, so if X is orientable 2 manifold, then it is the connected sum of several copies of torus. Okay, so whenever I want to sketch an orientable 2 manifold, then it will look like this diagram. Okay, so it's a very important result about 2 manifolds. Now let's talk about the fundamental group of these orientable 2 manifolds. So if I have a 2 manifold of genus G, then its fundamental group is generated by A1 B1 up to AG BG, and the relators, the relator is going to be the product of expressions of the following form. Now we know that A1 B1, so commutator of A1 B1 is basically A1 B1 and A1 inverse B1 inverse, and this expression is basically the product of all commutators is equal to 1. So in other words, we can write this down as A1 B1 product up to so on AG BG is equal to 1. So in particular, if we have G is equal to 1, or in other words, we are talking about a compact connected orientable 2 manifold of genus 1, or simply we know it as 1 torus or a surface with 1 hole. Okay, so if G is equal to 1, then the fundamental group of this X is basically generated by A1 B1 such that the commutator of this A1 and B1, okay, so A1 B1 commutator is equal to 1. In other words, we say that A1 and B1 commute. Okay, so A1 B1 A1 inverse B1 inverse is equal to identity implies that A1 B1 is equal to B1 A1. So in other words, we can say that the fundamental group of this is basically the free abelian group of rank 2, and that's what we have already seen. Okay, and similarly we can go on and we can calculate the fundamental groups of other surfaces. So in this way we can calculate the fundamental group of every compact connected orientable 2 manifold. Okay. So if X is non-orientable 2 manifold, then it is homeomorphic to the connected sum of copies of real projective plane, and here G is called the genus of X. And let's see what will be the fundamental group of this non-orientable 2 manifold. So the fundamental group is going to be equal to this. So basically generators are C1 up to CG, and the relator is going to be the product of the squares of these generators. Okay, so let's see when this G is equal to 1. So this G is equal to 1, and let's see what will be the fundamental group. So in other words, we are talking about what will be the fundamental group of real projective plane. Okay, so the fundamental group of the real projective plane is going to be equal to, so here G is equal to 1, so there will be only one generator such that C1 square is equal to 1. Okay, so from here we can see that the fundamental group of real projective plane is going to be equal to cyclic group of order 2. Similarly, we can construct, we can see other examples. So for example, what will be the fundamental group of Klein bottle? We have seen that if we take the connected sum of two real projective planes, then it's going to be Klein bottle. Okay, so let's see the fundamental group of Klein bottle. Okay, so let's call it K. So it's connected sum of two copies of projective plane. So we need two generators, C1 and C2, such that C1 square and C2 square is equal to 1. So this is the finite presentation of the fundamental group of Klein bottle. And similarly, we can go on and we can construct other fundamental groups of non-orientable compact connected 2 manifolds. Now let's continue with our second section of today's lecture, which are CW complexes. So CW complexes are basically generalization of simplicial complexes, or in other words, we can say that every simplicial complex is going to be a CW complex. We shall see. So how we define CW complexes is basically a step-by-step process. So in the step number 1, we choose some zero complexes or zero cells, or basically just collection of points. And in the next step, we attach 1 cells to these 0 cells. And in the next step, we attach 2 cells. In the next step, we attach 3 cells, and up to so on. So that's how we construct a CW complex. Okay, so we know, of course, what are 0 cells. This is just points, and we know what are 1 cells. Okay, so remember the definition of n cell. Okay, so it's basically just an open disk. So 1 cell is basically just going to be an interval and ignoring the endpoints. Okay, and similarly we can construct a 2 cell. A 2 cell is basically an open disk, so a disk without the boundary, and up to so on we can construct we can construct 3 cells, and up to so on. Now what does this procedure means? So for example, using this procedure we can construct a torus. Okay, so to construct a torus, we start from 1 point. Okay, so just 1 0 cell, and then we attach 2 circles with it. Okay, so this is called the wedge product. We will define it formally in our today's lecture. Okay, so attach 2 1 cells. So what are the 1 cells? So we have already seen that a 1 cell is basically just this open interval. Okay, so just this D1 minus this S0. Okay, so S0 is 2 points, and D1 is this interval, a disk of length 1 inside R1. So this is 1 cell, and attach 2 1 cells to this 0 cell, which is a point, and we will get this shape. Now attach a 2 cell. Okay, so what is a 2 cell? 2 cell basically it's take this disk and ignore the boundary. Okay, so in other words, D2 minus S1. Okay, so in topology, when we are saying that do some procedure, so we assume that this for example this disk is made of rubber. Okay, so you take this open disk which is made of rubber, and then stretch it such that you connect it to these two circles in a way that we obtain a torus. Okay, so this is our first circle, and this is our second circle. Okay, so these are our circles, and we attach the two cell and we obtain a torus from it. So that's how we obtain a torus using this procedure. So in other words, we can say that a torus is a CW complex. So before starting with the formal and precise definition of CW complexes, we will need some machinery from topology again. Okay, so we are going to define weak topology. Okay, so how we define a weak topology on a space X? So assume that the space X is covered by the subsets AJ's, that is X is equal to union of these sets. Now such that these AIs satisfy the following condition. Number one, each AI is a topological space. Number two, whenever they intersect, okay, so let's say this is AI and this is AJ. So on the intersection, their topologies agree. In other words, the open sets of AI are the same as open sets of AJ on this intersection. And the third condition is for each JK, the intersection AJ intersection AK is closed in AK and AJ. Okay, so for example, if this is AJ, this is AK, so whenever there is an intersection, then this set is basically closed in AJ, because AJ is a topological space, and this set is also closed in AK because AK is also a topological space. Okay, so then the weak topology on X, determined by this collection of subsets which basically cover the whole topological space, is the topology whose closed sets are those subsets F for which F intersection AJ is closed in AJ for every J belongs to capital J. So that's how we define a weak topology. So first take a set, cover this set with the collection of subsets such that X is equal to union of those subsets. Each set is a topological space, they agree on the intersection, and the intersection is closed in the respective topological spaces. Then the weak topology on X is a space where the sets are closed if their intersection with these AIs is closed for every J. So that's how we define a weak topology. Okay, so let's consider some examples of weak topology. So consider a family of topological spaces. So the co-product, okay, so the co-product, we have already seen it, we have already used it, this notion of co-product is disjoint union equipped with weak topology. Okay, so determined by this. Okay, so when we are taking the co-product of different topological spaces, we can say that these collection of topological spaces cover the whole space, and these Xi's are also topological spaces, and they are disjoint. So basically they agree on their intersection, and the intersection is also closed in each and every of them. So all the conditions are satisfied. So that's why we can say that we have a weak topology on the co-product of topological spaces. Okay, so let's consider another non-trivial example where we are going to define the wedge product of topological spaces. So it's the same wedge product that we have already used, where we constructed the wedge product of two circles when trying to construct a torus as a CW complex. Okay, so how we define the wedge product of different pointed topological spaces. Okay, so for example, I have one circle which is a pointed topological space in a sense that I have one point marked on this circle, and I have another circle which has one other point marked on it. Okay, so we have S1 and S1, so let's call it X0, let's call it Y0. So I have two topological spaces. Now we define the wedge product denoted by this, which is the quotient of the co-product of these two topological spaces in which the base points are identified. Okay, so just take the co-product, but in that co-product identify the base points, in other words identify these 2 points. So basically we obtain a space like this. Okay, so this is S1 wedge S1. Okay, so similarly we can calculate the wedge product of let's say 10 circles, and similarly we can construct the wedge product of 2 spheres, for example. Okay, so sphere is a topological space, mark a point on it, take another sphere S2, mark a point on it, and then identify these points in the co-product. So what we will obtain is basically a space like this. Okay, so similarly we can construct the wedge product of other topological spaces. So that's the example which we have already seen, which is the wedge of 2 circles. Okay. Now we need to recall this definition of an n cell. We have already seen that what is a 1 cell, what is a 2 cell, and what is a 3 cell. So in general an n cell is basically a homeomorphic copy of the open disk. Take dn and take out this Sn minus 1, so which is the boundary of the disk. Okay, so what is going to be a 1 cell? So take this d1, okay, and take out these boundary points. So S0 is basically these 2 points, so let's call them P1 and P2. So 1 cell, let's denote it by E1. So E1 is basically D1 minus S0. Similarly, what is going to be a 2 cell? So this diagram shows it all. So take a disk and take out its boundary, then we will get a 2 cell. Similarly, we can calculate, or we can see what it is going to be a 3 cell. So a 3 cell is basically a 3 disk and take out the boundary. Okay, so D3 minus S2, and similarly we can go on and try to and we can define and we can see what is an n cell. Okay, so let's go on with our discussion and our aim of defining precisely what is a CW complex. So we need another definition. So assume that a topological space X is a disjoint union of cells. Okay, so what is a cell? We have already seen it, and we are not mentioning the dimension of these cells. So these cells could be of any dimension. So the point is, this X can be written as union of those cells. So the K skeleton of X is defined as set of all cells whose dimension is less than or equal to K. Okay, so if a space can be covered by many cells of various dimensions, then what we are doing is, in a K skeleton we are writing down all those cells whose dimension is less than or equal to K. Okay, so and then we have this filtration. Okay, so of course if we are considering x1 and we are considering set of all cells whose dimension is less than or equal to 1, then of course it will contain the 0 cells. And similarly, if we are considering a 2 skeleton where we are taking set of all cells whose dimension is less than or equal to 2, then it must contain x1 and x0, or set of all cells whose dimension is 1 and set of all cells whose dimension is 0. Okay, so we can easily see that this X is going to be the union of these K skeletons. Okay, so now we are ready to define a CW complex. Okay, so a CW complex is an ordered triple. We have a space X, we have collection E of cells, and we have some morphisms. So let's see one by one. What are these objects? So X is a host of space, E is a family of cells in X, and phi is a collection of maps such that the following conditions are satisfied. So number 1, E is union of these cells. Okay, so remember or keep in mind the example of torus. Okay, so for each K cell the map is a relative homomorphism. So what is a relative homomorphism? So relative homomorphism from let's say from this pair to this pair is basically phi from x minus a to y minus b. Phi of course restricted to x minus a is a homeomorphism. So that's what it means by relative homomorphism. Okay, so it says that take sk minus 1 from dk. In other words, consider k dimensional cell, and it should be homeomorphism. Okay, so when of course when you take out this sk minus 1 from dk, then you will get a k cell to this space. So join a cell with the xk minus 1 and then take out xk minus 1. Okay, so in other words, roughly speaking, what we are saying is that the new cell that we are going to join is going to be homeomorphic to this k disk. Okay, so for each k we have the following map, and these last two conditions only matter if this set E is infinite. Okay, so otherwise it doesn't matter. So the conditions are, if we have a cell inside this capital E, then its closure is contained in finite collection of cells in E. X has weak topology determined by these closures of cells. Okay, so once again the axiom 3 and 4 only counts when E, the collection of cells, is infinite. Okay, so a CW complex is finite if E is finite, and if this is finite, then axioms 3 and 4 are redundant. So let's review again. Let's talk about the torus again and see how this is a CW complex. Okay, so in the first stage we have x0, which is collection of one point only. In the next stage we are going to attach two one cells to it. Okay, so let's go back and see the definition. So in the first case, it should be x should be union of all these cells, and of course when we are taking point and when we are taking these two one cells and then we are attaching these two cell to the wedge of S1 and S1, then basically we have E0 union E1 union E1 union E2. So this is definitely equal to the torus X. So the first condition is satisfied, and the second condition says that the thing we are attaching to xk minus 1 is homeomorphic to a k cell. Okay, so in each step whatever we are attaching is homeomorphic to a k cell, and it's also true in this case. In the second step we attached two one cells to this discrete set. Okay, so and each is homeomorphic to one cell, and similarly we continued and we attached a two cell with the wedge product of S1 and S1, so that's why the second condition is also satisfied. And once again these 3 and 4 doesn't matter because our E is finite. So in this case this E is basically this collection of cells. Okay, and the union of this is X, and that's how we obtain a torus as a CW complex. Similarly, we can go on and try to construct other complicated examples. For example, we can construct a 2 torus. So in this case, start from a 0 cell E0 and attach 4 circles to it. Okay, so when we attach 4 circles to it, then the diagram becomes something like this. So in other words, we have E1, E1, E1 and E1. Okay, and in the next step we attach a 2 cell to it. Okay, so when we are saying that attach a 2 cell, we know what is a 2 cell. It is basically an open disk, and consider this open disk is made of rubber sheet, and you stretch it such that you attach this sheet to this 4 circles, and we will obtain a 2 torus. So or we can say that fill the space between these 4 circles and we will obtain a 2 torus. Okay, so please notice the formation of these circles on this 2 torus. So this purple circle is going like this light blue circle is going like this, and this red circle is going like this, and this green circle is going like this. Okay, so this dotted means so it is going like this and taking a round about this torus. Okay, so write down or make the formations of your circle like this, and then fill the space between them, and you will obtain a 2 torus. So that's why a 2 torus is a CW complex. Okay, so if we have a CW complex, then X is called a CW space, and E phi is called a CW decomposition of the space. A CW space may have many CW decompositions. Okay, so we have seen just one example of CW decomposition of torus, and maybe there are many more CW decompositions of a torus. Now let's recall ourselves that when we constructed the projective spaces, then we have this result that complex projective space is equal to E naught union E2 up to so on union E to N. And similarly we also had this result about the real projective space. So Pn R is equal to E naught union E1 up to so on union En. Okay, so this tells us the following thing, that this real projective n-dimensional space has CW decomposition, which is given like this, and this n-dimensional complex projective space has the following CW composition, and this quaternionic projective space has the following CW decomposition. So if we have a CW complex and consider a subset E prime of E, and define this E prime mod is equal to the union of these cells. Okay, so basically when we take a subset of the collection of cells and then take the underlying topological space of these cells. Okay, so take their union. It's going to be a topological space, and it's going to be contained in X because X is covered by this E. Okay, and define this phi prime, which is going to be collection of all maps such that E belongs to E prime. Now we call this space a CW subcomplex, so where the topological space is the underlying space or the union of the cells, and E prime is subset of E prime, E, and phi prime is those morphisms which are associated to the cells inside E prime. Okay, if X is a CW complex and Y is a CW subcomplex, then their quotient is also a CW complex. Okay, so it's a theorem, and if you are interested in the proof, then you may have a look in Joseph Brotman's book on algebraic topology. So these are our references for today's lecture. Next time we will eventually start with the definition of cellular homology, and we will try to construct some examples, and we will see that it's relatively easy to calculate the homology when you consider the cellular homology. This is the end of the lecture. Thank you very much, and Allah Hafiz.